All right, here we are again for part 2. So, let's keep going. For the second part of the lecture, we are going to define normal and shear stress and determine the shear and normal stress at a point. So, let's see. Let's begin. So those are our learning objectives. We wish to define normal and shear stress and determine the shear/normal stress at a point along a member. Now, again, we remember our general analysis methodology. This is important to keep in mind as we go through this. We start with our external forces. And from these, we get our internal forces. And then from these, we get stress and deformation. And there is some interaction between these. And both of these are performance criteria, define what we call performance. And these often affect each other. Well, not that. That's a one-way arrow. That's a one-way arrow. Ah, I erased all my arrows. Okay. Two-way arrow and one-way arrow. Okay. So I need to define something known as a centric axially loaded member, or a CAL member. We will be using this quite a bit in this class, at least for the first portion of the class. So centric axially loaded member. A centric axially loaded member, or the CAL. Or the CAL. Okay. So what does this mean? Well, we need a member that is, say, homogeneous, has a constant cross-section, is also just an idealized, very uniform member. And then we have a load P on it on either end. We have only a tension load on either end of it, or a compression load, I suppose, would work just as well. But the key is this is loaded directly along the central axis of its member. Or, sorry, the central axis of its cross-section. So what do I mean by that? Well, let's say we have, well, it would be nice if we had, say, a nice doubly symmetric cross-section. That'd make things nice and neat. So say we had maybe just a solid, solid circular cross-section. Or maybe we could have a doubly symmetric W section. That would work nicely. And this point load P is going to be acting directly through the center of the member. That's where the centric axially loaded member comes from. It's going directly down the center of the axis. So let us look at what happens if we make some cuts on this. I want to do the same method of sections, but looking at various cuts on this member. So I'm going to consider two cuts, cut A, and cut BB. Cut B, like shown. So I'm going to do a free body diagram of each of these and analyze what kind of internal forces we have. So any questions on this so far? Okay. Let us look at cut AA. Cut AA. Hello, my name is Tanya Larson, and I have a mechanics of materials problem. Okay. So, yay, more bad jokes. Cut AA. So this cut is perpendicular to the member's section, or to the member's axis. And let me show the central axis of the member here. And we have a force P like here. And then I'm going to have my boundary forces. Well, let me show the cut here. So I'm going to have A, and I'll have a shear, a normal force, and a moment. Shear, normal force, and a moment. And notice I am drawing each of these assuming positive by our basic sign convention. Now, if we do a sum of forces on this, we will find that the normal force is equal to 0, or sorry, the normal force is equal to P, because if I do a sum of forces in the horizontal direction, I find the normal force is equal to P. The shear is equal to 0, because if I do a sum of forces in the vertical direction, there's nothing to resist that, there's no vertical force except the shear. If it's the only one, it has to be 0. Or if I do a sum of moments, I will find the moment has to be 0. So on a plane that is cut perpendicular perpendicular to the axis on a CAL member, the moment will be 0 and the shear will be equal to 0. Now, what if I have to cut BB, a cut that is not perpendicular? It's at some angle. Cut BB. So, and we will see actually, and put a little note here, that this is 0, 0 for all CAL cuts. Zero for all CAL cuts. Then we make cut BB. This one's at, I'm going to draw it at approximately a 45-degree angle, but it could be at any angle. Anything other than the perpendicular of AA. So let us show BB. B. And the forces, I'm going to have the axial force P. And then notice, this is my shear is perpendicular to my cut. So it's not, shear is not necessarily perpendicular to the member, it's perpendicular to the cut. Or sorry, parallel to the cut. The normal force is not necessarily along the axis of the member, it is normal to the cut plane. And the moment is just like this, as such. And so then, if I do a balance of forces, what do I find? Well, if I do a sum of forces, I don't have numbers on here, so I can't get an exact value. But if I do a sum of forces, say in the horizontal direction, I find that the normal force isn't equal to 0, because if I do a sum of forces in the x and y direction, I will find that both of these have to have non-zero components. It's the only way that's going to work. However, a balance of moments, we still have this center axis here. The line of action of P goes through the point that we're summing moments about. If we sum moments about this point here, the center of the beam, or the center of the member, all of these forces, the N, the V, and the P, all have lines of action that pass through there. Therefore, the M is still equal to 0. In a CAL member, the M is always equal to 0. Zero for CAL members. Okay, so we're still talking about loading, but let us look at transverse loading. Yes, transverse loading. So transverse loading. So say we have a transverse load at a cut, so this is not a CAL number. Let us say I have a cut AA. And also let us say that I have two loads P, and these are separated. They're not directly on top of each other, but they're separated by a very small distance. P, P, PP. So if I draw the cut, I will find, on the left side anyway, that there are the following forces. So this is cut AA. I have force P here. And then I have my shear, again, drawn with the correct positive orientation, normal force, and moment. Moment. And sum of forces in the horizontal direction tells us that n is equal to 0. That sum of forces in the vertical direction tells us that v is equal to p. And a balance of moments will tell us that m is approximately equal to 0. And this is assuming a small distance between the p's. This assuming small distance between p's. So basically these p's are small enough, are basically on top of each other. Not quite on top of each other, because I do want there to be some separation, so when I cut them, I only get one of them. But generally, this is shear, where you have a shearing, a separation of sections. This is the closest you can get to pure shear loading. Okay, now I'm done talking about types of loading for now. So let's talk about stress. Stress is this class. Okay, stress. What is stress? Stress. Well, stress, a good definition of it, if we're talking physical, not psychological, we're talking an engineering class again, not a psychology class, so we'll use the physical definition. Stress is a measure of the intensity of force. Of the intensity of a force. In units, force over area, like so. The units are PSI, KSI, newtons per meter squared, any sort of thing that's a force over an area or derivative of force over area. Kilonewtons, meganewtons, or megapascals, etc. That should be kilopascals. So in other words, it has the same units as pressure. Kilopascals, etc. And stress is defined as a function of two things, load and geometry. load and geometry. And namely, the geometry we're talking about is surface area at a cut. So stress is a function of load and geometry. It is determined by the load applied and the geometry of a beam or any member, a column, anything. But then, so stress is a function of load and geometry. But what about loads themselves? Force, loads, reactions, etc., are not a function of geometry. Pounds, kips, newtons, etc., are not a function of geometry. This is why when you learn to make shear and moment diagrams in statics, you didn't have to consider the geometry of the member. You did learn how to calculate, you did actually learn how to calculate centroids and moments of inertia and things like that. But to actually find the internal loads, like the internal shear, it's not a function of geometry. Let me show you what I mean. If we go back here to this problem, we found the internal forces in this member at point S, but I never even told you what kind of member that is. I didn't tell you whether this was a angle. I didn't tell you whether this was a W section. It could be a big wooden beam for all I care. I don't know anything about this. If I want to know anything about the stresses in the material, yes, then I would need to know the then I would need to know the actual geometry of the cross section. But since I didn't ask about the stress, I only asked about the loads, then we don't need to worry. We don't need to know anything about the geometry in order to find the loads. Now, I should couch this saying, in general, loads are not a function of geometry, but there are a few cases where they are, especially things like, the obvious example is probably something like self-weight. If you have a beam, well, if I make it twice as deep, it's going to be twice as heavy, and then it has to carry a bigger load. So in general, aside from things like self-weight, loads are independent of geometry, but you can probably think of some cases, and there are some other ones as well, where loads can actually be affected by geometry. Okay, so let's keep working at this. Joy. Let us look at normal stress versus shear stress. I need to define both normal stress and shear stress. Normal stress sigma. We use the Greek letter sigma. If this looks like a mutated 6, I'm sorry, it is a sigma. Okay, so now let me draw a mutated 3D diagram. I am not the best at 3 dimensions, so I'm just kind of muddle through it. So let's have this thing here. I'm going to have a cut here. And a beautiful 3D diagram. Like all my drawings, perfect in every way. Okay. So this cut is at a certain angle theta. So we're not considering just the perpendicular cuts. We have a local y-axis and a local x-axis. Y is along the cut, and x is perpendicular to the cut, like shown. And then I'm going to have a P here. And from here, I have a bunch of little stress arrows. All of these little pieces are little elements of force at each location along the beam. This is the stress distribution. And all of these together then come to form the overall N, the overall normal force at that point. Now the cut will have an area, and I'm going to say say a cut. And then a definition of sigma that I can give is sigma is equal to n over the area of the cut. N divided by the area of the cut. Okay, a few notes. For normal stress, direction is always perpendicular to the cut. Perpendicular to cut. And positive for tension, negative for compression. In other words, a physical property determines whether it's positive or negative. It's physical. We're saying tension is positive. This is a physical thing. Anytime you have tension, you have positive normal stress. Then we need to consider shear stress. And these are the two of the biggest things we're going to be working through in this course. Shear stress, the Greek letter tau. Now, some might pronounce it tau, but I was in a Greek organization in college, theta tau, and we were sure to pronounce it tau because that sounded fancier. So I'll be referring to it as tau in this course. So, but that's neither here nor there. If any of y'all would be interested in reviving the E.T. Tyler chapter of theta tau at some point, let me know. That's a pet project I'd like to see happen one day. But that's neither here nor there. There was a colony for a while, but it kind of died out. But anyway, that has nothing to do with mechanics of materials. So let me draw another mutated 3D diagram in my glorious handwriting. Oh, that looks terrible. Let me fix that. Okay. So let me do this here. More like that. Kind of like that. And there we can kind of get a 3D-ish shape. And we have a whole bunch of shear stress arrows, and these will come together to form the overall shear force. So we have the P here. We have many shear stress arrows. Many shear stress arrows across the surface of the cut. And all of these together combine to, along their centroid, to form, oh, there should only be one arrow there. We typically draw shear with half an arrow like that, V there. And again, this will have area, A cut. And the notation, or the formula, sorry, tau equals V over the area of the cut. Okay. Then a few notes. Direction is parallel to cut. And sign convention, rather than by physicality, sign convention and coordinate system determine positive or negative. So we just define shear in a certain direction to be positive or negative. And coordinate system. Determine, this looks terrible, determine positive or negative. Determine plus or minus. Any questions on that? Okay. And then let us look at the general state of stress. General state of stress. General state of stress. This is a stress block, something you'll see quite a bit of. I think I may have missed something back here. Let me double check something. General state of stress here. Let me check something really quickly. Nope, never mind, we're fine. Okay. The general state of stress here. Well, I'm going to draw a stress block. This is something that shows all of the stresses on a cut in an object. Or maybe not necessarily on a cut, all of the stresses on a object at a certain point, at a certain location. So I will have the x and y axis here. I'm going to make this a little bit bigger. I think this is going to be a little cramped if I do this here. I'm going to have the x and the y. My local x and y axis. And then I'm going to have sigma x and sigma x along the x-axis. And notice I'm going to be drawing all of these as positive. Sigma y and sigma y. Now the shear stress is going to be like so. Shear, 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 and shear. This is the tau xy or tau yx. These are the same thing. So the reason these are going to be like this is what's needed for equilibrium to be ensured. So they go for shear. You can read about this more in the book. I would encourage you to. But tau xy is tau yx, the same thing. And they're either, but in order to maintain equilibrium, they have to be one of two things. They're either tip to tip or tail to tail. Or tail to tail. In order to maintain equilibrium. Actually, both. They need to be tip to tip and tail to tail. So the alternate for negative shear would be them going down and over like this. That should be an and, or an or. And tail to tail. Note 3 stresses for 2D. For 2D, if we were in 3D, we would have 6 stresses. Sigma x, sigma y, and tau xy. Those are the stresses on a point. Okay. So let's see. Then I'm going to work through an example here. I have one more example that I'm going to work through finding a state of stress at a point. So this example, I'm going to have a truss that is cut out with the method of sections. State of stress in a truss member. In a truss member. And I may need another slide or two on here, but we'll see. State of stress in a truss member. Here. So we have the following section, and if you remember the method of sections, hope this should be very familiar. Pardon, my truss got erased. So this is cut out of some larger truss. So we would have, say, points H, F, Actually, let me do these in a different color. Uh-oh, I erased my line. Oh well. So I'm going to have points H, F, G, and then maybe I have point I here, and E. These are points. Then I'll do my forces in red. So I'm going to have a, let's say I have forces, a 15 kip force here, a 15 kip force here, or sorry, a 25 kip force here, and this is actually, sorry, upward. This is a load we're supporting, and this is a reaction at G. 25 kip force upward here. Then and then I cut it along this line here for the sake of finding these forces. So we have FHI, FI, and FEF, and FEF. And the distances, let me label some distances here. Let's say this is 8 feet, all this is 8 feet. 8 feet, 8 feet, and 8 feet. And I want to find the state of stress in a truss member EF. So we're given this, and given, find state of stress in member EF. Yeah, member EF. Okay, find the state of stress in member EF. So I'm going to need to give myself a little more room to work. So I'm just going to copy this one. We'll call this 13, and we're almost done after this. This is the last example I'll be working through today. Oh, and let me make sure still running here. We are good. Good, good. Okay. So I want to then go and say the first thing I need to do is use the method of sections. So the solution here. One, find force in member EF. Well, this is done by a balance of moments, by sum of moments at I. This will lead us to that FEF equals 35 kips tension. So you all know how to do that. I don't not necessarily feel the need to work through that. So you all learned how to do that in statics, but this is new here. So I'm going to take a variety of cuts to find the state of stress at a point somewhere in member AA. Now, let us consider cut AA. Or sorry, cut AA. Cut AA. All right, so I'm going to have the following. AA is going to be a perpendicular cut. And this member has a cross-sectional area of 4 inches squared. That doesn't mean all the cuts that we make will have a cross-sectional area of 4 inches squared, just that the minimum cross-section of this is 4 inches squared. It is impossible to cut this member and have any area less than 4 inches squared visible to you. AA, and the force is on here. Well, I have my 35 kip force here, and I have N, normal force. I have my shear, V, and a moment, M, like shown. And from this, I will determine the following. Via a balance of forces, it can very easily be shown, like we did earlier, that N equals 35 kips, and V equals M equals 0. Now, sigma is going to be equal to N over the area of the surface, or area of the cut, same thing, equals 35 kips over 4 inches squared equals 8.75 KSI in tension. So if I draw the stress block there, or the stress point, stress at this point, and tau equals 0. If I draw the stresses on here, I will see 8.75 KSI and 8.75 KSI, like shown. You got that? Okay. So 8.75 KSI tension and tension alone on this section. Next, I'm going to do two cuts, BB and CC, that are perpendicular to each other. So cut BB is going to work like this here. Cut BB. So I'm going to have the same member, but I'm going to cut it at a diagonal. The total area is going to be the same. This total area is the same, but the area of the cut is not going to be different. Equals 4 inches squared. And this means that I'm going to have the following. I'm going to have shear V, a normal force N, and I'm going to have let me label the cut, BB, like shown, BB, and a 35 kip tension force over here. Now, let me work through a bit of trigonometry. This is important to derive the formula that I'll be providing later. Oh, and let me provide the triangle here, the force triangle of this, or just the slope triangle. This is at a 4, 3, 5 triangle. So let me expand upon this and say that this cut, BB, let me put it over here a little more actually. So this cut here is like this. And along this cut, we're going to have both the shear and the moment. So we have V and N. And there is a right, oh, what did I do? Okay, we're good. And this is at a right angle here. And this is the same 3, 4, 5 triangle. 3, 4, 5. And then if I work through some trig here, Well, I'm going to have the horizontal angle here. So let's consider this right angle here, like so. Basically, these will come together to make the 35 kip force. Sort of the parallelogram rule here. So I'll have theta and alpha. And I can also extend the triangles here. So I have one down here as well. So I have a parallelogram. And this one comes to theta. And this one. This one comes to alpha, and this one comes to theta. So working through the parallelogram, I will find that n over 35 equals the cosine of alpha equals the sine of theta equals 4/5. V over 35 equals the sine of alpha equals the cosine of theta equals 3/5. And then finally, I need to find the surface area. Area of surface over 5 is equal to the total area over 4. So just the 3, 4, 5 triangle. And this can come to a surface equals 5 over 4 times 4 inches squared equals 5 inches squared. All right. And then the stress here, I will get the stress sigma. Sigma equals n over a surface on the surface equals 28 kips tension over 5 inches squared equals 5.6 ksi tension. And the shear stress, tau, equals V over a surface, the area of the cut surface, equals 21 kips, no tension or compression here, it's a shear, over 5 inches squared, equals 4.2 ksi. 4.2 ksi. Questions so far? Okay. Then cut CC. Our final cut. It's going to be similar but cut differently. It's going to be cut in the opposite direction essentially. It's going to be this is cut basically perpendicular to the other cut. So I'm going to shorten this a little bit because we're strapped for time. So let's say we have a CC here, CC, and I will have, let me look at a force triangle here, N, V, and all of this comes to the 35 kip force. In other words, they sum up to that. And this is theta, and this is alpha. Theta and alpha. And if I work through more trig, I get that N equals sine of theta times 35 kips equals 3/5 times 35 kips equals 21 kips. And V equals the cosine of theta times 35 kips equals 4/5 of 35 kips equals 28 kips. And the area is now is a different area this time. 5/3 times 4 inches squared is 6.67 inches. 6.67 square inches. And if you divide these by each other, you will get that the sigma is equal to 3.14 ksi, and the ta is equal to 4.2 ksi. Notice, it's the same ta as before. There's only one shear stress present at a point. So if I draw the overall state of stress, the overall stress block here, if I have these two perpendicular cuts, B, B, and CC, CC, I'll have these forces, or sorry, these stresses here. So I'll have 5.6 ksi here. Wait, yeah, that's fine. 5.6 ksi and 5.6 ksi. I will have the 3.14 ksi, the normal stress from cut CC, 3.14 ksi, and 3.14 ksi. And I will have a single shear stress going this way, this way, this way, and this way. Notice head to head, tail to tail. And these are all equal to 4.2 ksi. All the shears are going to be equal to 4.2 ksi. So finally, so that's the solution to that problem completed. Let me now write an in general condition. In general, if I have, so the general formula for this, if I have a P and a P, and I have a cross-sectional area, A transverse, so A trans, and let me say there's the axis of the member here. Let me call this angle phi, between the cut and the angle and the axis of the member. Well, in general, the formula for this is sigma equals, and the book will go over the full derivation of this, but you should get some hints of it here. P over transverse area, A trans, times sine squared phi, and ta equals P over A trans times sine phi cosine phi. And those are our general formulas for finding the state of stress in CAL members. All right, questions on this? All right, as a reminder, If you have any questions, feel free to email me. My normal office hours are 3 to 4 p.m. I can take calls then. Except today. Today was a weird day because of some technical difficulties. I'll be posting these lectures onto the website, which was where you're probably watching them right now. That should do it. I will talk to you all again tomorrow, and as always, thank you.